In this video, we're going to do an overview of the gas laws that we use in AP Physics, and this should be a review for you if you've already taken chemistry. So the gas laws that we're going to talk about are Boyles Law, Charles Law, the Gay-Lussac Law, and the Ideal Gas Law. One thing to keep in mind as we go through these is that for every single one of these calculations, Boyles, Charles, and Gay-Lussac, we really need to have the temperature be in Kelvin. Where Kelvin is Celsius plus 273. For the ideal gas law, it sort of just depends on what unit the gas constant is in, but most likely we will always have it in Kelvin. So just make sure that you're performing those conversions before you get started. So all of the first three gas laws, Boyles, Charles, and Gay-Lussac law, talk about the relationship of gas volume and pressure and temperature. And specifically, Boyles' law deals with just pressure and volume, assuming that we are keeping the temperature at a fixed level. So Boyles' law says that gas volume is inversely proportional to the pressure applied to it. So that basically means that as we increase the pressure, it's going to decrease the volume, or if we decrease the pressure, it decreases the volume. And you can see here, this is just a graph. This is actually a PV diagram, and we'll look at them more in depth when we talk about thermodynamics, because they're actually used to, sort of quantify and look at the amount of work that a gas might do. So you see here initially, if we have a pressure of 0.6 atmospheres, the volume of the gas is at 2 liters. But if we decrease the pressure to 0.3 atmospheres, we actually have the volume increase to 4 liters. Where this sort of comes into play in the sample that I'll give you on the homework assignment is looking into the pressure that a scuba tank would experience as it goes underneath the surface of the water. So we covered in fluid physics how to figure out the gauge pressure or the absolute pressure as someone dives underneath the water. So that would be an added amount of pressure that would be acting on the volume of gas in the scuba tank. So actually, as you go deeper down in the water, the volume of the air within the your container, your scuba tank, actually gets smaller because we've increased the pressure. So volume and pressure are inversely proportional. If we look at this, mathematically we could say the initial pressure times the initial volume would be equal to the final pressure times the final volume. And just to give a basic example, it says you have a sample of chlorine gas and you go from 946 milliliters to 154 milliliters, and the starting pressure is 726 millimeters of mercury. What would the final pressure be? So if we look at our variables here, again, remember they're inversely proportional, so we can kind of make an estimate to begin with. So the volume has decreased to 154 milliliters, so that means that the pressure must have gone up. So algebraically, we have this, and I won't go through all the steps. This is AP Physics. You should be able to do the algebra. We see, yeah, that does make sense. There is a lot of more pressure added when the volume has gotten smaller. All right, the next law is Charles' Law, and Charles' Law relates the variables of volume and temperature. So gas volume and the temperature of the gas are directly proportional to one another, so that means that the greater the temperature, the greater the volume of the gas, or the less the volume of the gas, the less the temperature. And the example that I have here is a combustion engine, and so, and we'll look at this also more in depth when we look at thermodynamics, but you can see here, this chamber right here is the combustion chamber. So as you drive a car, the gas comes into the combustion chamber, and then the spark plug ignites it. And when the spark plug ignites it, it actually causes this gas to expand as it heats up, right? So it heats up and it gets bigger, which forces this piston to move down because it's taking up a greater volume right here. So it forces this piston to move down and then swing around and then push back up, and then forces the gas out in the exhaust valve. Okay, so that's sort of like an oversimplification, but an application of Charles' Law. So they're directly proportional to each other. So if we look at that mathematically, V1 over T1 is equal to V2 over T2. And then just an example, and keep in mind what I said on the very first slide, that we need to always have our temperature in Kelvin. So in this problem, it says you've got a gas is 3.2 liters at 125 degrees, and then you want to know what the temperature is when the volume is decreased to 1.54 liters. And again, remember that this is assuming that the other variable of pressure stays constant. So if we list our variables, note here that I've added 273 to the temperature in order to get it in Kelvin, and I can kind of make a very simple estimate because I know they're directly proportional. If I start with 3.2 liters and I go down to 1.54, which is about half, that means the temperature is going to be cut in about half too, so I'd expect it to run somewhere around 200 Kelvin. And if we algebraically solve that for T2, plug in our values, we should get, there we go, 192 Kelvin, about what we estimated. All right, the Gay-Lussac law then relates pressure and temperature to one another, assuming that the volume is fixed. So pressure and temperature, you can see from the equation, just like Charles' law, that is a relationship that is directly proportional. So as the temperature increases, then the pressure increases, and as the temperature decreases, the pressure decreases. So let's kind of go back to talking about kinetic molecular theory and how we define pressure in the first part of this unit. So remember that according to kinetic molecular theory, the temperature of something really is a measure of the average kinetic energy of the particles, right? So we have all of these particles bouncing around within a container that make up the gas, and the hotter they are, the faster they're moving, and therefore they are colliding within the container with a greater amount of energy. So then let's remember what pressure is. Pressure is force per unit area. So if you have molecules that are moving a lot faster because they're a lot hotter, they're going to have more energy, and therefore they're going to strike the walls of the container with more force. So it does make sense from both a Gay-Lussac law of pressure and temperature being directly proportional, but also looking back at that theoretical kinetic molecular theory and just the definition of what pressure is. All right, now for every single one of those laws that I've covered so far, we're assuming that one of these variables is kept constant. So for Boyles Law, the temperature was constant. For Charles, the pressure was constant. And for Gay-Lussac Law, the volume was constant. But in actuality, we can have all of these three variables changing at once. So if we do not have any of these fixed, then we would just use this relationship of PV over T equals to PV over T to figure out the changing pressure and volumes or temperatures under those conditions. All right, the last gas law that I'm going to talk about is the ideal gas law. And if you recall from chemistry, if you've taken it, the ideal gas law allows us to not only look at the pressure, the volume, and the temperature of the gas, but also the amount of gas. And the amount of gas is measured. So the amount of a substance, there's lots of different ways that we can measure this. So one way is volume. Another way is in moles, which is the SI unit for the amount of a substance. We can also express it in terms of the number of particles that make up the substance or the mass that makes up the substance, right? But moles is really the SI unit that like unifies the different quantities. And again, I'll kind of go through this very basically on the next slide just as a reminder from chemistry, but you know, hopefully we have taken chemistry and know this a little bit more detail. I'm just kind of trying to breeze past it. So the ideal gas law says that the pressure times the volume is equivalent to nRT, where N is the number of moles that make up a gas, and R is the gas constant, the universal gas constant, and T is the temperature. So keep in mind that from chemistry, we learned that the mass of any mole of a gas is what the periodic table says. So for helium, if we looked on the periodic table, the mass is 4 grams. So 1 mole of helium gas would have a mass of 4 grams. If we're talking about oxygen gas, the mass from the periodic table for oxygen is 16. However, oxygen is a diatomic, so that means that it always comes in little pairs. So 1 mole of oxygen gas would be 32 grams. The gas constant, we use a universal gas constant in physics, assuming that we're using the SI unit for pressure, which is in kilopascals, and so the unit is 8.315 joules per mole times Kelvin. Again, note that you need to have your temperature in Kelvin. In chemistry, we had different R's dependent on what the pressure was, but we always assume in physics that we're going to be using the pressure in our SI unit. All right, so if we can look at the ideal gas law in terms of moles, we can also look at it in terms of a molecular form. So it looks pretty similar, but we have a couple of different variables in there. We still have the pressure and the volume and the temperature, but we have a different N and a different constant, which is K. K is Boltzmann's constant, which is 1.38 times 10 to the 23rd joules per Kelvin. And this we discussed, or you may have seen when we looked back at heat and the kinetic energy of molecules in the first video of this unit. And N in this case, this uppercase N, is actually the number of molecules. So this is where we get a little review from chemistry, where we have the lowercase n, right, is moles, and the uppercase N is the number of molecules. So if we take the number of molecules and we divide by Na, which stands for Avogadro's number, that will tell us the number of moles. So just remember that there's 6.02 times 10 to the 23rd molecules or particles that make up a mole of any substance. So using this ratio here allows us to convert back and forth between moles and molecules.